are going to move on to the sections after Cauchy's integral formula. So before moving into lemma 2.7, we'll just see some among the ideas of how we can represent 1 by w minus z, where z is a point coming from modulus of z minus a strictly less than r, that is an open disk with center a and radius r, and w is on the boundary of the circle. Modulus of w minus a is equal to r, that is it is a circle centered at a with a radius r, and w happens to be on the boundary. So w and z are chosen likewise, and we are going to see if we can get some kind of a power series representation for the form 1 by w minus z. So here 1 by w minus z can be written as 1 by w minus a into 1 divided by w minus a minus z minus a the whole divided by w minus a. And you can see when you use the cancellations and simplifications, you get this is equal to 1 by w minus z. That is nothing but 1 by w minus a into 1 divided by 1 minus z minus a divided by w minus a. So both are the same. That's what we are saying. So you can equate this, the term sitting here to the term sitting here. Okay. And here we can use the geometric series here. Why? Because we know modulus of z minus a divided by w minus a will be strictly less than r by r, that is equal to 1. So you can use the geometric series here. Okay. What is there to note? Here we have to note that modulus of z minus a divided by w minus a will be strictly less than r by r, which is equal to 1. So you can, instead of 1 divided by 1 minus the term which is this, which has its modulus strictly less than 1, you can use the geometric series, which is nothing but summation n is equal to 0 to infinity z minus a divided by w minus a whole raised to n. Okay, instead of z you have the term here. Of course you know that 1 divided by 1 minus z is equal to summation n is equal to 0 to infinity z raised to n whenever modulus of z is strictly less than 1. That is the part which we used here. Okay, and you got the term sitting here and the term sitting here. We are going to multiply both sides by f of w divided by 2 pi I, and then integrate, use the line integral around the circle gamma, which is this integral over gamma f of w divided by 2 pi I into 1 by w minus z dw is equal to integral over gamma f of w divided by 2 pi I 1 by w minus a into summation n is equal to 0 to infinity z minus a divided by w minus a the whole raised to n into dw. And from Cauchy's integral formula, which we had earlier seen, here you can take the 1 divided by 2 pi I out, and then you are left with integral over gamma f of w divided by w minus z dw, that is nothing but f of z by Cauchy's integral formula. And on the right hand side you have a big term here. So what can we do for this right hand side? In order to simplify it, we might need to interchange the summation and the integral. So let's see how we can do that using lemma 2.7. Lemma 2.7 says that let gamma be a rectifiable curve in C. Uh, that means you know about the bounded variation and all of that. And suppose that Fn and F are continuous function on the set gamma. On the set gamma, that means it is a trace, which means the points of the curve. If capital F is equal to u minus limit Fn on the trace of gamma, then integral over gamma is equal to limit integral over gamma Fn. That means the limit and the integral can be interchanged. That's what it says. So this is nothing but limit n tends to whatever call it n, limit over n fn is equal to limit integral fn. That's what over gamma. That's what it says here. That means limit and integral can be interchanged. Okay, suppose if epsilon is greater than 0, we know that epsilon by V of gamma, which is V of gamma is a total variation, that will be strictly greater than 0. Since Fn's and F are continuous and F happens to be the limit of Fn, okay, then you get modulus of Fn of W minus Fn of W is strictly less than epsilon by V of epsilon for V of gamma for every W on the trace of gamma and n greater than or equal to capital F. There exists such an n. Okay. Now you're going to take the modulus of integral over gamma F minus integral over gamma Fn. That is equal to we are taking the integral out using the property of the integrals. You get that is equal to modulus of integral over gamma f minus fn, and using the property and interchangeability of integrals and modulus, you can write that is less than or equal to integral over gamma modulus of f of w minus fn of w modulus of dw to make it more rigorous. And we know that this modulus of f of w minus f and w will be strictly less than epsilon by v of gamma. You can use it there. And integral over gamma modulus of dw will be the total variation v of w. So you get epsilon by vw into vw, and you get epsilon there. And epsilon is strictly greater than 0 and it's arbitrary. So you get that integral over gamma f is equal to limit of integral over gamma fn. Okay. So this simply means that f is the limit of fn. That's what means here. Okay. So that's how we can end up the lemma which says the integral and the limit of the functions that can be interchanged. Okay, next is the very important theorem of the section which says about analytic functions having a power series representation, and that is theorem 2.8 with the statement f being an analytic function in open disk BAR, then f of z is equal to summation n is equal to 0 to infinity a n into z minus a the whole raised to n for modulus of z minus a is strictly less than r, where a n is equal to 1 by n factorial into nth derivative of f at a, and this series has radius of convergence greater than or equal to r. So you have to understand that what is given to us is that f is analytic in this open disk. Rest of it you have to prove out. Okay, so for that let r small r be such that 0 strictly less than, small r strictly less than capital R. Capital R is already with us in this open disk. The radius is that. So this means that the open disk with centered at R and centered at A, and this radius small r will be obviously containing the A of capital R. That means they are concentric. Concentric. Concentric circles. So suppose if it happens to be like this, if this is some A, this will be BA of small r, this will be BA of capital R. Okay. If gamma of t is equal to a plus r e raised to I t, where t happens to be ranging from 0 to 2 pi, then by our Cauchy's integral formula, we know that f of z is equal to 1 by 2 pi I integral over gamma f of w divided by w minus z dz for every z which happens to be inside modulus of z minus a strictly less than r, right? This is simply the gamma of t is simply a circle which centered at r and centered at a and radius r. So this is the parametric representation of that. Fine. Now, since modulus of z minus a is strictly less than r and w is lying on the boundary of the circle gamma, we have something useful. We are going to take the modulus of f of w into z minus a the whole raised to n divided by w minus a the whole raised to n plus 1. Consider this. Okay. That will be less than or equal to some quantity. Uh, we are assuming that this modulus of w minus a is equal to r. Okay. So you get modulus of f of w to have some maximum value on that boundary. Okay, that let that be m, so that is less than or equal to m into modulus of z minus a the whole raised to n divided by modulus of w the whole raised to n plus 1. Okay, right? So you can substitute instead of w modulus of w minus a, you can substitute for r, and what you end up is a value like this. Okay, now you're going to think about the Weierstrass M test, which we usually use in such situations. Here you have some fn's, right? When n is ranging, call it fn. That then call it modulus of fn. Okay, that is less than or equal to some quantity mn, and n is also varying, right? And this quantity necessarily will be a converging quantity because of oh yes, there is here you have r and so you get that to be m by r. Okay. Okay, so you are getting such a quantity, and that always happens to be uh, its summation is strictly less than infinity. The quantity is sitting here. Okay, so using Weierstrass M test, we can say that the summation of the function inside this modulus, that is summation f of w z minus a the whole raised to n divided by w minus a the whole raised to n plus 1, converges uniformly in the area we consider, that is for every w which is happening to be coming from the points inside gamma or the trace of gamma. Okay, now you have to use the Cauchy's integral formula, which says that if z is happening from inside the desired domain, you get f of z is equal to 1 by 2 pi I integral over gamma f of w divided by w minus z dw. And earlier, while we started this lecture, we said that 1 by w minus z has the possibility to be written like this. Okay, you're going to substitute that here because all the assumptions there are satisfied while we were proving here. So instead of this 1 by w minus z, you are substituting its equal term, that is 1 by w minus a into summation n is equal to 0 to infinity z minus a by w minus a the whole raised to n dw. Okay, and here from the earlier section you know that the limits and integral can be interchanged, so even if it is an infinite sum, it can be interchanged, summation can be taken out, and you get what happens to be this. Okay, so you are going to call this one as an. Okay, so you obtain f of z is equal to summation n is equal to 0 to infinity a n into z minus a the whole raised to n, where a n happens to be this number for every n. Okay, and okay, so here we have one more thing to note. The preposition 2.5 in the earlier chapter 3, which said that if f of z is having the power series representation with the radius r strictly greater than 0, then it has a, b, c, and the c is that a n is of the form 1 by n factorial into f n of a. So that applies here by that preposition, since all the hypotheses there are satisfied. Yes, the function is having the power series representation, and the series is converging inside modulus of z minus a the whole modulus of z minus a strictly less than r. That means a n has the form fn of a by n factorial. So each a n will be independent of z, and it is independent of the set of points in gamma, and it will be independent of r. And since r was chosen arbitrary, which is strictly less than capital R, the series representation holds for all such z which happens to be from the open disk modulus of z minus a strictly less than r, and the radius of convergence of the series will be uh, at least R. So that's the very important theorem which helps us to understand that every analytic function in such an open disk will be having a corresponding power series representation like that. So thank you for watching out this video. Thank you.